Welcome to the 8th pre-recording of the Programming Languages Virtual Meetup. My name is Connor Hoekstra, and in this pre-recording we're going to be covering Chapter 2.4 of the Structure and Interpretation of Computer Programs. The chapter is laid out in the following way. It's entitled Multiple Representations for Abstract Data, and the three subsections are Representations for Complex Numbers, Tagged Data, and Data-Directed Programming and Additivity. We'll start off with the first subsection, which introduces the concept of complex numbers. The textbook starts off by stating, we have introduced data abstraction, a methodology for structuring systems in such a way that much of a program can be specified independent of the choices involved in implementing the data objects that the program manipulates. The textbook then goes on to state, but this kind of data abstraction is not yet powerful enough because it may not always make sense to speak of, quote, the underlying representation, end quote, for a data object. For one thing, there might be more than one useful representation for a data object, and we might like to design systems that can deal with multiple representations. The authors in the text then go on to introduce complex numbers, specifically that there are two different ways of representing complex numbers. Those two different representations being the rectangular representation and the polar representation. So we have seen this diagram multiple times before. We have our procedures for manipulating these. We'll have some selectors and constructors, and then the representation underneath. The text then goes on to show that we can have two different types of constructors, one that takes as input the two components, a real component and an imaginary component for the rectangular representation, or we can take a constructor that takes magnitude and angle, which is for the polar representation. But we can have these constructors for both representation and just do some transformation based on which one we are choosing to store our representation as. So you can see here are the procedures that we're going to use to manipulate our complex numbers. It's just highlighting that it doesn't matter which representation we use, we can implement both. So the first two are working with the real and imaginary components, whereas the second two are working with the magnitude and angle components. It doesn't matter which representation we use, we can still define these procedures. The next two pieces of code that I'm showing are the textbook basically pointing out the different selectors and constructors that we are going to use depending on the representation. So the key point here is if you look at the last two procedures here, these are the constructors. And so this is for if we're choosing the rectangular representation. You note that when it's calling the constructor make from real imaginary, it's just doing a cons because we don't need to do a transformation here. But if we're provided with a magnitude and an angle, then we need to do a transformation because we're choosing to store using the rectangular representation. But on the next slide, we see the opposite. So we once again have two constructors, make from real imaginary and make from magnitude angle. But for the magnitude angle one, we're now just doing cons because we don't need to do a transformation because we're storing it as the magnitude and angle. But for the make from real and imaginary, we have to do a transformation because we're not storing it using the rectangular representation. We're storing it using the polar representation. And that's basically it for the first section. It's just introducing to you this notion of complex numbers and that there are two different ways to represent these. The next section goes on to talk about this tagged data technique, which gives us the ability to attach tags to certain procedures so that we can utilize different representations depending on what we want. So the first thing that this subsection introduces is these three procedures: attach tag, type tag, and contents. Attach tag is used to basically attach a tag to a procedure. And the last two, type tag and contents, are basically just wrappers around car and cdr. It's checking, is it a pair? And if so, it basically just passes you car and cdr of datum. Otherwise, it just errors out with this message. Now, using this type tag procedure that we just defined, we can now define these predicate procedures, rectangular and polar question mark, to check if we have a tag attached that corresponds to either the rectangular or polar representation. Once we've done this, you can see that we can now, in our constructors that we saw earlier, we can call the attach tag to basically attach a tag to each one of these constructors. And here you see that because we have the polar constructors, we're attaching the polar tag using the quote to use the polar symbol in order to basically quote unquote tag these constructors. So I'm only showing attaching the tag for the polar constructors here, but we would do the exact same thing for the rectangular representation ones, which the textbook shows. And once we have this, we can now dispatch basically using these predicate procedures, rectangular question mark and polar question mark, to get the corresponding selector, constructor, or procedure that we want when using complex numbers. So it's checking, do we have a rectangular tag here? If so, call real part rectangular. If that fails, then we go on to the next clause, which checks, do we have the polar representation? If so, invoke this real part polar. So using the predicate procedures, we basically dispatch the corresponding procedures for the representation. Otherwise, we hit this final clause that says we don't know what representation you're trying to access. And this modifies the diagram that we saw before, which basically says, we didn't have these combined dispatching to the two different representations. So now we've got two different representations, and with this tagged data technique, we can now dispatch to whichever representation we want, which is pretty neat. And that takes us to the end of the second section, and the final section shows us basically an even nicer way of doing what we just did. So the textbook states the general strategy of checking the type of a datum and calling an appropriate procedure is called dispatching on type. This is a powerful strategy for obtaining modularity in system design. On the other hand, implementing the dispatch as in section 2.4.2, the previous subsection, has two significant weaknesses. One weakness is that the generic interface procedures, real part, imaginary part, magnitude, and angle, must know about all the different representations. For instance, suppose we wanted to incorporate a new representation for complex numbers into our complex number system. We would need to identify this new representation with a type and then add a clause to each of the generic interface procedures to check for the new type and apply the appropriate selector for the representation. Another weakness of this technique is that even though the individual representations can be designed separately, we must guarantee that no two procedures in the entire system have the same name. This is why Ben and Alyssa had to change the names of their original procedures from section 2.4.1, which was the first section that we looked at. So this Ben and Alyssa part is a little bit confusing because I haven't touched on it, but basically in the textbook, they're using this story of Ben wanting to use the rectangular representation and Alyssa wanting to use the polar representation. And in the second subsection, when we're using tag data, when we're dispatching to the corresponding procedure based on the tag, we have to make sure that none of the names of our procedures collide. Otherwise, we're going to end up with compile issues. So this chapter basically points out these two weaknesses, and in the previous section, it even talks about additivity and basically how this is what this first paragraph is addressing, is that our system is not additive and that anytime we want to add something, we have to go update every single procedure. And so this section basically shows us a way to do dispatching that scales very nicely and is additive. And it basically has to do with like setting up a hash table or some sort of way of storing your operations and then placing using tags and an identifier for the operation into this hash table, or whatever representation you're using to store these, so that you can have an operation and type table to do lookup on and then do your dispatch there. And if you use this sort of install packages, you can also avoid the name collision, which I don't really do for the exercises because it adds a bunch of boilerplate. But this is it's a very nice trick, and I believe I skip in what the text covers for the complex number, and we just go to the first exercise of this chapter because it's pretty illustrative of this technique, and that's what the first exercise is asking us to do. So exercise 2.73 states section 2.3.2, that was what we covered in last week's video, described a program that performs symbolic differentiation. And this is what the textbook initially gave us. So you can see that we are performing differentiation, and we're doing a kind of dispatch where we're checking if we have a number, a variable, a sum, or a product, and then based on these clauses, whichever is satisfied, we then perform our differentiation based on those clauses. The question goes on to read, we can regard this program as performing a dispatch on the type of the expression to be differentiated. In this situation, the type tag of the datum is the algebraic operator symbol, such as plus, and the operation being performed is deriv. We can transform this program into data-directed style by rewriting the basic derivative procedure as follows. So this is basically the procedure we just saw rewritten. You can see that we still have the number and variable clauses, but other than that, we just have an else clause that's calling this get on the deriv tag, and then it has the operator of the expression, and then this is going to return us a procedure from our hash table, which is then going to be applied to the operands of our expression, and we're performing our differentiation still with respect to var. And we have these sort of operator and operands just defined as car and cdr. So the question is broken down into A, B, C, and D. And the first part, A, states or asks, explain what was done above. Why can't we assimilate the predicates number and variable into the data-directed dispatch? Well, I sort of answered the first part already. We're just, we folded our sum and product dispatch into these, and it's just going to be doing a lookup from a hash table. As to why we can't assimilate the predicates number and variable, so this is the answer that I have, and the tail end of it, it's basically that we don't have any tag to dispatch on for those. So for sum and product, and in the future exponentiation, we have the plus, we have the asterisk, and we have the caret, which are basically our tags to dispatch on. But for our variables and our numbers, we don't really have anything specific to dispatch on. So we can't. Moving on to the next two parts of question or exercise 2.73, B and C, we'll do these at the same time. So B states, write the procedures for derivatives of sums and products and the auxiliary code required to install them in the table used by the program above. And C, choose any additional differentiation rule that you like, such as the one for exponents in exercise 2.56, and install it in this data-directed system. So we sort of avoided the quote-unquote installing part, but we are going to be adding them to the hash table. And because we did the exponentiation differentiation rule previously in exercise 2.56, that's the one that we chose. So we're basically just going to take the code that we had from the previous video from last week, and we're going to modify it to use this sort of data-directed style. So this is the code that we had originally. Everything above my cursor was given by the book. Everything below the cursor was what was defined for exercise 2.56. So we have the make sum rule, the make product rule, the make exponentiation rule. Note that we have removed the predicate procedures because we're not going to need those once we are doing dispatch using our get and put methods. And this is the modified code. So previously in the deriv procedure, this is where the corresponding code for deriv sum, product, and exponentiation went. We would have our predicate procedures that was sum question mark, product question mark, and exponentiation question mark that would then invoke this code. We've taken these out and now defined them as their own separate procedures. So we have deriv-sum, deriv-product, and deriv-exponentiation. Other than that, the code is exactly the same. And once we have these as separate procedures outside of our generic deriv function, we can then use put to basically put these into our hash table. So we have basically two things that form our key. We have the deriv, which is going to be used to identify that this is what we're doing. We're using this with our derivation. So deriv is what's called, if we go back to our original or revamped deriv procedure, you can see here the tag we're using to look up the procedure to call here is deriv. So we put these in with deriv, and then the second part of our key is going to be basically the tag. So for sum, we're using the plus. For product, we're using the asterisk. And for exponentiation, we're using the caret or the hat. And then this is the boilerplate code for get and put. We have our table, which is going to be our hash table basically, and then we have put and get, which are using the two keys as to basically set up our key for our hash table, and then get and put call the respective hash set and hash ref functions or procedures in order to get this to work. And then we show our previous revamped deriv procedure that we saw before. And so this is basically old code. And note that in order to get this to work without having to change my original code from exercise 2.56 from last week's video, I had to drop the cdr from exp because the previous code is expecting a list that starts with the tag. So you don't need to do this. Ideally, you could have just kept the cdr here. I would have had to go on and modify my code, though, such that you're dropping the tag at the beginning of my expression. Whereas if you just leave it there and ignore it, you can reduce the number of changes that you have to make. And at the bottom here, we just have a bunch of unit tests checking that x plus 3 gives us the coefficient of 1 in front of the x. X times 3 gives us the coefficient 3 in front of the x. And then x to the power of 3 gives us 3 times x to the power of 2. Which is what we'd expect when performing differentiation with respect to x on all of these expressions. And last but not least, for exercise 2.73, sub-question D states, in this simple algebraic manipulator, the type of an expression is the algebraic operator that binds it together. Suppose, however, we index the procedures in the opposite way so that the dispatch line in deriv looked like the following. So it just basically swapped operator and operands, or no, sorry, it switched the operator exp with the deriv tag. What corresponding changes to the derivative system are required? It's pretty straightforward. You just have to swap key 1 and key 2 in your get procedure, and then you're done. So it's basically just changing the way you construct your key. So if you just swap these two, which I haven't here, in your get, it'll work. I'm pretty sure. Moving on to exercise 2.74, this is a very long-windedly stated question, but we'll read through it. It states, Insatiable Enterprises, Inc. is a highly decentralized conglomerate company consisting of a large number of independent divisions located all over the world. The company's computer facilities have just been interconnected by means of a clever network interfacing scheme that makes the entire network appear to any user to be a single computer. Insatiable's president, in her first attempt to exploit the ability of the network to extract administrative information from division files, is dismayed to discover that although the division files have been implemented as data structures in Scheme, the particular data structure used varies from division to division. In a meeting of division managers, a meeting of division managers is hastily called to search for a strategy to integrate the files that will satisfy headquarters needs while preserving the existing autonomy of the divisions. Divisions' personnel records consist of a single file which contains a set of records keyed on employees' names. The structure of the set varies from division to division. Furthermore, each employee's record is itself a set, structured differently from division to division, that contains information keyed under identifiers such as address and salary, in particular. And then that's an odd way to jump into the question. But the first question is similar to the last question. It's broken down into A, B, C, and D. So the first sub-question, A, asks, implement for headquarters a get record procedure that retrieves a specified employee's record from a specified personnel file. The procedure should be applicable to any division's file. Explain how the individual divisions should be structured, in particular, what type of information must be supplied. So this is a very, very confusing, sort of long-winded question. So the first thing that I did was I just set up sort of two different quote-unquote record sets for two different divisions. So it's not super complicated, and we're assuming that each division or the company across all divisions has unique names for their employees. A more realistic way would be that every employee had a unique employee ID. But for simplicity's sake, we're just assuming that there's only one Bob at Insatiable, there's only one Jen, etc. And you can see that for Division A, we sort of have a structured list for each employee. So Bob is a list. There's a list that starts with sort of the key Bob, and then there's a bunch of pairs, one for address, one for salary, that you can do lookup for. But for Division B, we just have a flat list that we know that sort of based on some schema, which you can see above. The first thing is the name, the second thing is the address, and the third thing is the salary. So not super realistic, but we have two different representations for two different record sets across two different divisions. So this is my answer to question A. I've defined these two procedures for convenience. One is for finding an element in a list, which makes use of memf. The difference between memf and findf: memf returns the whole list after the found element. Findf just performs a car on that list to get just the element, and car equals is just checking to see if the first element of a list is equal to whatever you're checking. So for each of these record sets, we can actually use basically the same thing to get a record back because they are both indexed with the first element of the list basically being the name of the employee. So we can just perform a find if, checking to whether to see the first element of each of these sublists, so each of the records is equal to the name we're looking for. Then we put the A and B records with the corresponding names. So here you can see we still have to name these differently. That's one of the issues that section or subsection 3 points out. If we hadn't done the sort of installing package trick that the textbook points out, we would avoid this, but this is a little bit simpler. And once we have this, then we can define, so this is the actual answer to the question, this define get record procedure. It takes a div, which stands for division, and takes a name, which stands for employee name. And we'll do a lookup on the hash table that is storing the corresponding procedures for Division A and Division B. So we pass it whichever division we want, and then the name. So if we make a call to get record for Division A and Jen, it'll return us the record from the Division A record set. If we make a call to get record for Division B for Jim, it returns us a corresponding record for Jim that exists from the record B record set. And we move on to sub-question B, which states, implement for headquarters a get salary procedure that returns the salary information from a given employee's record from any division's personnel file. How should the record be structured in order to make this operation work? So here's my answer for question B. So here you can see this is where the implementation differs between looking up the salary because of the difference in structure of the two different record sets. We'll start with record B. So here I'm just defining the procedures inline using sort of lambda. I could have named these and then passed in the name, but both work. So here we're basically just doing cadatter. So we're trying to get the salary, and if we scroll back, you can see here that the salary is the third item. So we want to do a cdr, and then car. And because we read from right to left, we end up with cadatter. So cdr, car. And then we put this in with a tag B and then the procedure tag salary. For A, it's slightly more complicated. We do a lookup, and for both of these, we first have to get the record before we get the salary. So we do a lookup on the record, then we do a cdr to drop the name because then we'll be left with a list of pairs. Then we do a find F to find the pair where it is contains the salary information. Note that we can't use the trick of it just being the third pair or the second pair, because you can see for Bob and Jen, they have their address and salary stored in reverse order. So if Bob has his address first, then his salary, whereas Jen has her salary first and then her address second. Notes, I got too many S's there, so that's a small bug, but c'est la vie. And so once we've found the salary, then we just do a cdr to basically cdr down to the salary and then a car to get it out of the list. And then we put this into our hash table with the tag A and the procedure tag salary. And then once we do this, we define a very similar procedure to get record that is just get salary, that takes a division and employee name, and then gets the procedure from our hash table using the div and salary tags, and then applies that to our employee name. So if we do get salary on division A for Jen, we get 150,000, and if we do a get salary division B for Anne, we then get 250,000. So hopefully this makes a little bit more sense than just abstractly showing you this two-line definition of get salary and get record. Moving on to sub question C, implement for headquarters a find employee record procedure. This should search all the division's files for the record of a given employee and return the record. Assume that this procedure takes as arguments an employee's name and a list of all the division's files. So this question is pretty straightforward. If you were able to make it through the first two, it's basically going to be a recursive call to looking for the record in a given division. If you don't find it, you're just going to recurse or cutter down your division list until you do find it, and if not, you'll fail to find. So that's exactly what we're doing here in our find employee record procedure. It takes the name of the employee you're looking for and your division list. The first thing you do is an if expression, checking in your predicate whether the div list is null. If you get to this point, you weren't able to find an employee, so technically I should maybe wrap this in an error, but it'll just return you a string here. If your predicate fails, that means you have a non-null list, so you move to the alternative statement. Here we have a let star where we define div to be the car of div list, so just the first div that we're looking at. And then we store in our temporary a call to get record of div and name. So basically we're checking to see, is this employee in this division? If this returned something, you basically just return the record. Otherwise, it returned false, and you want to make a recursive call to find employee record and just cutter down the div list. And like I said, if you get to the point where your div list is null, you failed. Otherwise, at some point, you are going to find the record corresponding. And this works. So if you make two different calls, find employee record Jim with the div list AB are two divisions, it'll give you Jim's record. And if you do the same thing with Jen, it'll get Jen's record. And note that Jim is from division B and Jen is from division A, but it was successfully able to find both of the records. So pretty neat. And last but not least, when Insatiable takes over a new company, what changes must be made in order to incorporate the new personal information into the central system? It's pretty straightforward. Just add get record and get salary plus the corresponding put methods to add them to the hash table, and you're good to go. And I guess there's technically one extra thing that in any of your calls to procedures that take a division list, you need to add, C, D, E, and all the other division names. So probably a good idea to just have a master list of this instead of this all over the place where you can just update it once and then you're good to go. And then we get to the final sort of part of the last section of this chapter 2.4, which talks about this technique of message passing. So the textbook states the key idea of data-directed programming is to handle generic operations in programs by dealing explicitly with operation and type tables, such as the table in figure 2.22. The style of programming we used in section 2.4.2 organized the required dispatching on type by having each operation take care of its own dispatching. In effect, this decomposes the operation and type tables into rows, with each generic operation procedure representing a row of the table. An alternative implementation strategy is to decompose the table into columns, and instead of using quote-unquote intelligent operations that dispatch on data types, to work with quote-unquote intelligent data objects that dispatch on operation names. We can do this by arranging things so that a data object such as a rectangular number is represented as a procedure that takes as input the required operation name and performs the operation indicated. In such a discipline, make from real image could be written as the following. So here we have a procedure called make from real image. So this is the analog of our constructor. But instead of returning a sort of data structure, it's returning a procedure. So make from real or imaginary is a higher order procedure in that it's returning a procedure, and this procedure that returns is basically performing dispatch. So you're going to ask, what kind of operation do you want to perform? It gives you all these tags for quote-unquote operations that you want to perform. And then when you get this in the future, this is what it'll do. So if you pass it real part, it'll return you the real part of your number. So this is the equivalent. The real part and the imaginary part are the equivalent of your selectors. And then the magnitude and angle are the equivalent of your selectors that do the transformations. So this is pretty neat, and it's a little bit hard to recognize, but basically message passing is what Alan Kay introduced when he popularized object-oriented programming. So this, in a sense, is sort of the classes that we know in our modern, Java, C++ languages, and these are the methods that comes with these class. And the textbook states that, we're not going to look at this right now, but we're going to come back to this later and show how it's a very powerful technique. Which brings us to the final exercise that we're covering, exercise 2.75. Implement the constructor make from mag ang, which stands for magnitude and angle, in the message passing style. This procedure should be analogous to the make from real imaginary procedure given above. This is pretty straightforward. You're basically just copying and pasting and then modifying the little bits. So we have our selectors, and the transformations happen in the real part and imaginary part instead of the magnitude and angle ones. And that is it. I don't have anything to comment from the MIT lecture because the corresponding lecture to this chapter didn't actually focus on the text at all. It focused on implementing a pattern matching engine in Scheme. So it was an interesting talk, but not really relevant to the chapter 2.4 that we covered in this video. And that is it for today's pre-recording. Hopefully you enjoyed and learned something. I will be back next week with coverage of chapter 2.5. Hope to see you then.